How's it going, guys? So what we're looking at today for physics vids is question 46 of chapter 33. This guy's dealing with a partial loop and the B field felt at the center of that loop. The couple things that we need to notice right away are that first of all, this loop is in a plane. So where sometimes we have a point out here that we're calculating the B field at. In this case, the point is all the way in here. So it's just in a plane. And also we need to recognize that where the charge comes in, where the current enters and leaves the loop is directly in line with P. So it doesn't contribute to the B field at all. That's because you get a value that is, when you do your R cross your velocity of I, you're just gonna get a sign of 0 or a sign of 180 in there as your value for this cross product, and that goes straight to 0. So those guys don't contribute at all. There's two equations that we're going to be dealing with in this. First one is this B field for a pretty much for a loop of charge, or for a loop of current, and what it's doing is taking your test point, which is somewhere out here, some distance z from the center of the loop, and calculating the B field that it experiences as a result of current passing through this wire here. In this case, we just talked about this being in a plane. Our test point P is directly at the center, so we're going to go ahead and get rid of this z value because it's 0. So we don't have to worry about that. It's all the way at the center of the circle. So that's one nice thing we can get rid of right away. And then what we kind of understand this for a little bit more of an explanation about this, just trying to keep track of time here and not hold you guys too long. I'm going to refer you to Bensky's video on deriving this equation from the Beyond Savart law, and you can find that on his YouTube channel. Also, the other equation that we're going to be using is this guy, and this is the simplified version of pretty much the simplest case scenario for this is where z is 0, so it's a loop in a plane, and also we're going around the full loop. So we don't have to worry about just going around a fraction of the loop like we're doing over here. We're not integrating. We're integrating from 0 all the way around to 2 pi, ending at the same part. Where here we're going to integrate from 0 to some theta. And that's the same theta as we see here, kind of representing how far around that loop you're going to go. First thing that we want to do is we want to start modifying this equation for our B field. The first thing that we know is that it's no longer BZ, because BZ is saying that there's a point out here and it's Z distance from the center of our circle. We're not worried about the distance because it just is 0. So we have mu naught, which is our constant, times I, times r squared, which is the radius of this loop. We're going to have 4 pi in the denominator. That just gets carried along and is canceled out when we multiply by mu naught. And then we're multiplying by 0 squared plus r squared, all raised to the 3/2. We see something nice happen here right away. We have r's in the numerator and r's in the denominator. We're going to see some canceling happen. This is all just going to go to mu naught I divided by 4 pi r. You kind of see this happen because when you raise an exponent, when you raise an exponent to another power, you're just going to multiply those two powers to get a simplified, and this is just going to be 0, so we don't worry about that. We can now bring in this exponent into the parentheses. Then we get a cubed in the denominator and an r squared in the numerator. We just get rid of the r squareds in the numerator and just keep 1r in the denominator. Now this guy is still multiplied by our 0 to theta, d theta. So pretty much what happens now is when you integrate this guy, you're just going to get out a theta, and theta is going to be in radians. And what's going to happen is we're going to get B equal to mu naught I times 4 pi r times theta. Now theta is going to create, with 4 pi in the denominator, it's going to create some fraction, a fraction of the total loop, and that's going to modify the B fields, so it'll change the magnitude of the B field depending on how much of the loop you're integrating across. Now that we have this guy, we can go ahead and we can run a check, which is part B of the question, and that's asking, does your result agree with the B field of the current in the loop if theta is 2 pi? So throwing in 2 pi for this value, pretty much our hope is that we come out with this equation over here, because we already checked. We know that this is, in the book, this is the equation for a full loop of charge testing a full loop of current testing the B field at the center of the loop. So we're going to go ahead and we're going to plug in our 2 pi. See how this goes. B equals mu naught I over 4 pi r times 2 pi. Now that boils down to, we get to cancel out the 2 in the numerator, bring it down to just a 2 in the denominator, get rid of both of the pi's, because there's one in the numerator, one in the denominator, and we just divide by 2r. We see that that works out pretty nicely, really simple form, and it does in fact check with that guy. So that's question 46. I hope it was a little bit helpful, and good luck on your final.